Good afternoon, everyone. Welcome back to the spring semester of the Research Exchange series here at CITRIS. We're really delighted to have you with us. I'm Camille Crittenden. I'm Executive Director here at CITRIS and also co-founder of the CITRIS Policy Lab and the Women in Tech Initiative, which you'll hear a little bit more about. We're really pleased to have Rama Akkiraju here from IBM to launch our spring series in the Research Exchange. And I'll make just a few brief remarks before I introduce Rama. Today's talk is co-presented by the Women in Tech Initiative, which has a number of activities going on this semester, which I'll tell you a little bit more about as well. The initiative is one of 6 of CITRIS's research initiatives. It's devoted to promoting the equitable participation of women as benchmarked against the participation of men in the tech industry with regard to career longevity, career progression, career pathways, and recognition. And it's especially appropriate that Rama is our speaker today. She was featured in our annual symposium last year, which was devoted to women in AI, the future of AI, and women in technology. And she will also be recognized in our event in early March as winner of the Athena Award for Executive Leadership. So we're really pleased to have her here. Just a couple of quick announcements before I give a little bit more background about Rama and the talk that you'll hear today. The next Research Exchange series, this is a weekly event, as you probably know, on Wednesdays at noon here in the Bonato Auditorium, but also webcast and then archived on our YouTube channel for later reference if you'd like to refer your friends to previous talks. The Research Exchange series has been going on for 10 years now. So we have really quite a nice archive of interesting and insightful talks that have been presented here on this stage. So next week we'll have a speaker, Vincent Van Hook from Google Brain, who will be talking about closing the perception actuation loop using machine learning, new perspectives and strategies. As I referred to earlier, I'll also encourage you to take a look at the Women in Tech symposium that's coming up on March 6th. Its theme is Reimagining Cybersecurity for All. So that will be a really great event held in Sibley Auditorium right next door with a really amazing lineup of panelists and keynote speakers. I encourage you to take a look at that. And we will also be presenting the Athena Awards, as I mentioned, sprinkled throughout the day. Rama Akkiraju, our speaker today, is an IBM Fellow, a Master Inventor, an IBM Academy member, and a Director at IBM's Watson Division, where she leads the AI operations team with a mission to scale AI for enterprises. Rama also heads the AI mission of enabling natural, personalized, and compassionate conversations between computers and humans. In her career, Rama has worked on agent-based decision support systems, electronic marketplaces, and semantic web services, for which she led a W3C standard. She has received a number of accolades from the popular press as well as more specialized and scholarly publications. She was named by Forbes as one of the top 20 women in AI research in May 2017, has been featured on the A-Team in AI by Fortune magazine in July 2018, and named one of the top 10 pioneering women in AI and machine learning by Enterprise Management. She's co-authored 4 book chapters and over 100 technical papers. She has 18 issued patents and 25 or more pending. She's received a number of Best Paper Awards and has served as president of ISIP, a service science professional society, in 2018, and continues to actively drive AI projects through this professional society, which is also one of the co-sponsors of the Women in Tech Symposium coming up in March. So please join me in welcoming Rama.
Thank you. Thank you, Camille. Can you hear me okay? Hi. Hi, everybody. It's a pleasure to be here, actually a pleasure to be back here at Berkeley. Of all the talks, presentations I give, I very much look forward to the ones that I give at universities because it gives the pleasure to go into richer and deeper conversations. And I'm very much looking forward to that after the talk. Hopefully there will be a good interaction session and questions after the session. So today what I wanted to talk about is the work that I do at IBM, which is making AI work for enterprises. So clearly I'm calling out enterprises, not just saying how to make AI work for everybody. So there must be something different about making AI work for enterprises versus making AI work for consumer applications, for example. So I want to call out what those differences are and what makes it different. I wouldn't necessarily say harder, but it's harder in several ways probably, but different in many ways. And talk about some of the best practices that we've learned after having tried to apply AI to enterprise kind of problems. And that's what I'll take you through today. So we all know that AI is all pervasive. We use it whether or not we explicitly acknowledge it. AI is there in our cars, in our phones, in our homes as devices that we are interacting with, and children are starting to interact with AI in terms of toys and the educational tools that they have at their disposal. Various tools that are helping us around the house, including robots that help clean the house and companion robots and so on and so forth. They're there everywhere almost, and they're making their way into many other aspects of our life. So these are examples of AI in our as consumers in our day-to-day lives, right? But AI is also making its way in enterprises. Clearly, as users of these enterprises services, we are on the receiving end of things. But we are also starting to see more and more of these applications that companies are starting to roll out, that we are starting to experience as the users of their products. Right? So, for example, chatbots or conversation bots, where you call into a customer support center, and on the other side is a bot. Either it is a chat bot or a speech recognition based bot that is able to, virtual agent that's able to respond to you in speech. Or it is doctor's assistants or nurses' assistants, radiologists' assistants. There are different kinds of AI applications that are making their way in healthcare, or legal assistants to attorneys and to people in the legal domain, basically helping them pour through these large volumes of documents and helping them prepare their arguments for their legal cases. Or in social media monitoring, where people are chatting about their preferences, their interests, their likes, dislikes about products, and companies are starting to tap into that data to better understand who and what the preferences of their customers are, to better segment and to reach out to their customers in very unique ways. And there are so many other applications in retail, very personalized sort of recommendations that are being made by retailers to individual buyers, and autonomous cars and face recognition technology that you're starting to see in airports and in security and other places, and so on and so forth. So there are many of these kinds of applications that enterprises or companies have started to roll out as part of their AI initiatives. Now, you could argue that even in the past there actually has been AI throughout, and there is digitization has happened at least 2-3 decades ago now, you could argue. And there are AI applications that so for example, that were there that did basically scanning your invoices and optical character recognition, right? So that has been there for quite some time. And more recently, towards the end of that corner, I've shown some applications that are starting to actually get into some of more touchy areas, where AI is helping screen job applicants, AI is helping make predictions about whom to give loans to and whom not to give loans to, and so on. So these, I would put them in the category of decision support systems. In some cases, they are even being deployed as systems that are making decisions. And that leads to a whole suite of ethical and legal questions around AI and all that. We could get a little bit into that. But the AI is starting to make its way into many enterprise applications. So what I wanted to talk about is kind of just go through and level set, so we are all on the same page on some of the terminology that I'll use and what do I mean by an AI model. And then I'll talk about, for enabling the applications, the kind that I just talked about, what does it take? What are the considerations that a company that's deploying such an application needs to be thinking about to make sure that it is not only addressing the needs of the consumer, but also it's auditable, it's secure, it's robust, and all of the considerations that that enterprises need to have when they roll out these kind of AI-infused applications. So how many of you are computer science, machine learning, data science background folks in the audience? If you can show me by. Okay, several of you. So you would have very good background about this already. So I'll go through this quickly. AI is not necessarily equivalent to machine learning. Right? AI is a broad field. It has a lot of other sub-disciplines in it: natural language processing, knowledge reasoning, and so on and so forth. People tend to equate AI with machine learning. So first of all, let's set that that it's not the case. I'm going to talk about AI models in broadly, but also specifically talk about machine learning models. And wherever I'm talking about non-machine learned models, I'll call out, say for example, applying natural language processing models or others. Typically, if you talk about machine learning models, if not all of the AI models, some of them are machine learned. And so let's first just look at this small segment of the models. Machine learned models require data to train, right? So I'll just set this some of the basic tenets of building an AI model, more specifically a machine learned model. It requires data, and data is the fuel, algorithm is the engine. Of course, you give the labeled data, it learns the patterns, and it is able to make predictions. Now, in that scenario, data is the biggest elephant in the room, right? Those that have the largest amount of high quality labeled data are the ones that can win in this race of building a very high quality AI model, right? And there are, people talk about these numbers all the time, and with my own first-hand experience, I can vouch for this. 80% of the time is spent in collecting the data and cleansing the data, preparing the data, and governing the data and managing that data. It's only the rest of the time that really then is spent on actually building the model, fine-tuning it, deploying it, and so on. So data is always the biggest pole, longest pole in the tent and the biggest elephant in the room. And it, depending on what kind of model that you're trying to build, it could be very costly. So I'll take, for example, let's take the customer support bot, that example that we talked about. Let's say it's a virtual agent. That means it's able to interpret what you are asking for, your support question, in natural language, listen to your speech, interpret the intent, and understand what you said, come back with a response, and respond back to you in natural language, that is speech, right? Let's just go through that one example alone and parse it to see what all kinds of AI models have to come together for that to happen. So first of all, when you are calling, you are talking in your language, so there is speech. That speech needs to be translated into text. So there is speech to text AI model behind the scenes. And speech to text AI model, there is a long history and tradition of how good are they, what does it take to train a model to build a speech to text model in different languages, in all the languages that humans speak. So that's one model. Then behind the scenes is the intent recognition. Once you have the text, you need to be able to understand that the person is calling about some network problem or a password reset problem, or what is the problem that the person is calling with. So parsing that text to really understand the intent behind that. So that's, you can call it an intent recognizer or some kind of a classifier. So there is another AI model there. Then there is figuring out, based on that intent, what response to give, kind of an AI model. So that could be a knowledge repository search, or it could be a deeper discovery in a set of enterprise documents, whatever the case may be. So that is an AI model. Then there is, once the information is retrieved, there might be a need for summarizing it, because it could be a long document that was retrieved. Summarize something out of it, something concrete. And then there is the round tripping part, which is once that information is succinctly retrieved or formulated, it needs to be translated into text to speech. That text needs to be converted back into a spoken speech, and that is what comes back to you as a virtual agent. So these many AI models, speech to text model, intent recognition model, then the discovery / search model, then there is the text to speech model, and then there is some kind of a dialogue management that needs to manage the entire process. So these are all the AI models that are behind the scenes. And now I'll take you through the behind the scenes of each one. Requires specific kind of data and amount of data for it to work at the level of accuracy that needs to work in order that that whole round trip works. And when the system is actually translating that text into speech, that it's not some gibberish response, and it's something really meaningful that addresses the problem that the user called with, right? So in order for that to happen, every model along the way has to have good amount of accuracy, and that accuracy can only be achieved when it is trained with the right amount of data by exposing it to the right kinds, right varieties of data and so on. So data always tends to be the longest pole, and we'll take each one of those and see. Now if you look at the data in an enterprise, broadly we can classify it into these three kinds, right? Structured data, semi-structured data, and unstructured data. Structured data is the kind that has always been looked at more traditionally from an information management, from databases perspective. There's been a long history and tradition in this space with very, I would say, pretty mature set of products in the market, although there is always more work happening. What kind of data is that? Let's look at it. The examples are, these are transactional data, typically like sales, customer service records, HR payroll data, metrics, if it is an AI, if it is a system, IT system or some kind of a system that you're monitoring, and finance data, all kinds of data that you can structure and put it in databases type of things. Semi-structured data has some loose structure. These are like tables in PDF, the Word documents or spreadsheets or the logs that systems write out, or the alerts or the HTML files, XML files. There is some structure, but within that structure there could be a lot of unstructured stuff in there. Unstructured data is this really untapped, typically up until now, could be in any kind of format, shape, and such, PDFs, Word, presentations, blogs, plain text, and all sorts of things. Typically, if you look at an average enterprise, they have a fairly good set of models to tap into that structured data, not so much in the semi-structured and unstructured. That so happens to be only 20% of enterprise data. Actually, 80% of the data is really semi-structured and unstructured. And the problem and the challenges with dealing with semi-structured and unstructured data are multifold. That first of all, the data could be very private and it cannot be exposed even within the boundaries of an organization. One department to another department, a lot of times there are constraints and they cannot expose it. It's not often labeled. Nobody in a table, the schema, the column name is your label. So it's right there. Exactly, you can go write an SQL query to pull data record corresponding to that column if you want it. But whereas if you are talking about unstructured data, unless you label it, you don't know what it is about or what it is, what parts of it is talking about what, and oftentimes it just gets generated, it gets stored at the very best, but there is no labeling there. If there is no labeled data, as is, it's a hard problem to really tap into it because you don't know what it is about, right? And it cannot leave premises, and there is some metadata ontologies about it may not exist. So lots of challenges. Although data is the longest pole in the tent, and there are different kinds of data, there are many challenges around data still. So I'll talk about some of the building blocks of AI, building AI models. So in the customer support example, I already kind of took you through the round trip of what all models are involved: speech to text. There is intent recognition, text to speech. Along the way, natural language parsing and understanding and recognizing different aspects of the text that the user has spoken. What's a noun, what's a verb, what's an action, which noun is acting on what other objects, and what is the connecting verbs, and all of those things, and what are the relations, keywords, and so on. And the search and retrieval we talked about, image recognition, dialogue manager we talked about, and then all these other things about that other services that may help you to understand the user better so that you can do more personalized responses. That may apply in specific situations like in retail, where you are calling about a product and you look for opportunities to upsell to that person. And in order to do so, you really want to understand that person, their preferences. And that could be services like understanding their communication tones. Are they in distress? Are they in a good mood or bad mood, so you know whether to upsell or not. Or what is the personality of that particular person, and so on. So there are many building blocks that are available, but to really kind of build that, let's continuing on with this example of customer support bot. If we take that, many of these building blocks need to be put together and assembled in a workflow for it to come alive. And I want to talk about that workflow of one AI model first. Then we'll talk about the workflow of all of them coming together. for that one model, we talked about data as the starting point, right? If we look at, so let's first look at this circle, and then each one has a different life cycle of its own. We'll go through the details. There is data collection preparation. For those of you who are doing machine learning and data science, and you are quite familiar with this process, this cycle, right? After you collect the data and prepare the data, you do feature preparation, then you do model training, you package it, you test it, benchmark it, deploy it, and then you continuously keep on improving it. So it's a life cycle. Now each one of this has a life cycle of its own. Data, you crawl, you cleanse and store, analyze and all that, and the features that you prepare, you got to specifically look at, do I tokenize it, do I segment it, what is the parts of speech lemmas, all those things you prepare. If it is speech, you prepare phonetic dictionaries and prepare this data. The model training itself has a life cycle of its own in terms of what algorithms to select, how to fine tune them, what architecture do I use for my algorithms, and how do I handle the edge cases, what training platform do I use, PyTorch versus any other options that are available, TensorFlow and so on. Testing has its own life cycle in terms of what do users think, keeping the provenance of the model and so on, and use crowd workers or people who label the data play a significant role in this whole life cycle as well. So this is the life cycle of one model, right? So let's now talk about what is the life cycle and what are the specific I would say attributes or characteristics of an application that you would build by pulling together multiple AI models, or it could even have even a single as a singleton one AI model, but then there are around this model, that's around this AI prediction model, which is either built with a singleton AI model or multiple AI models that have been assembled. There are a whole slew of considerations beyond just the ones that we have talked about around data, model training, testing, deployment, and so on. That's just the beginning of it, right? Of getting the model to actually be ready. Once it's ready, what are the things that you need to worry about? This is a mnemonic I coined to make it easy for us to remember the things. Each letter stands for a particular facet of the attributes of a model that we need to pay attention to. So let's look at that. What does that race and facts expand to? I didn't order them. That's because I would like to go through it in this order, but each letter you pull them all together and you'll see race facts. But it's accuracy of the model, whether or not the model is able to continuously learn in the environment. Is the model consistently improving, or is it improves in one iteration and degrades in another iteration? Security and privacy is important. Is the model fair? Is it transparent and explainable? Is it accountable? Is it auditable? And is it robust? Now, these are at least some of the important ones. There may be others that we can think about, but at a high level, definitely these set of things facets are extremely important from what we have noticed when companies want to deploy AI applications. So I'll take you through each one of these and some of the, I would say, strategies that we have evolved for ourselves to tackle each one of these things, and would love to hear your perspectives after that. So let's talk about accuracy. Accuracy of an AI model, as several of you would know, are measured in using different metrics. Now, some of the metrics that typically are used are precision, recall, F-measure, mean absolute error. If it is speech type of technologies, that you are looking at the word error rate or sentence error rate, and so on. I'm not going to spend more time in actually digging into the details of how each one is computed. Several of you may know already. If not, I'm sure you can look it up. But these are quality metrics that are typically used to describe the accuracy of a model. Typically, it goes on a scale of 0 to 100 or 0 to 1, and you're trying to kind of quantify the quality of the model. So I want to give you one example from a speech recognition system. So say this is speech to text model, AI model, that has been fed in with this dictation by a doctor. Okay, so doctor is using the speech to text model. So usually they spend a lot of time typing after a patient, they see a patient. So the speech to text system can significantly help them in reducing that time, right? So they could just speak into it, and it takes notes, and it gets added onto the medical records of the patient. So in this text, so the doctor is talking about a whole bunch of things you can read, but I don't want you to spend all your time reading. It's okay. There is some stuff going on with this patient. The ones that are highlighted are the ones where we've noted that the system actually made mistakes. The speech to text system actually heard them wrong. It wasn't able to actually translate them. So there is somewhere in here saying the patient is experiencing this discomfort on her lower sternum, is what the doctor said, and it noted it as stardom. So we're talking about accuracy. So I'll talk about the implications of that accuracy, and that's why I'm kind of giving you this example. Somewhere in here it said slightly elevated troponin is the protein that the doctor was referring to, and the system somehow transcribed it as proponent. Having a good Con-R syndrome, it's a coronary syndrome supposed to be. So again, it got it wrong, and this is something to do with some colitis or some such, and it got it wrong. So for the most part, it found things, but then there are mistakes, and these are captured as word error rates, and accuracy of the model is captured based on this. If you know the exact ground truth, which is what should be the actual transcript from that speech of the doctor, you compare that with what the system came up with, and you compute the overall accuracy, and you say these are the mistakes that the model made. Therefore, it's overall accuracy is maybe 85%, something like that. So yeah, so these are the mistakes that the model made. Lower sternum should have been lower sternum, proponent should have been troponin. This should have been a acute coronary syndrome. It got it wrong. Ulcerative colitis was or full sort of colitis. Now the question is, for any typical AI model, it's nearly impossible to get 100% accuracy, and more so to have 100% accuracy on day one when you deploy it in a particular environment on a particular domain problem. And unless you do something very elaborate training on that particular domain, on that particular customer's, client's data, training the model with that particular doctor's voice, and so on and so forth. So that is the problem that I want to highlight here, that typically an AI model is built like speech to text or text to speech or a natural language recognition sort of things by training it on a generally available set of data. Could be speech that's obtained from say media, from newsreaders, things, whatever we can get hands on, the vendors can get hands on, companies who are building those models can get hands on, get it over a period of broad variety of data, get it from multiple sources and train the model. That is called what we call as base model. I'll come back to that picture in just a bit. That we call as a base model. So the base model is the one that you build with whatever data you can get access to. But what happens is that because that's broad, solving a broad AI problem where you have to solve the speech recognition, let's just keep it for English for the time being, where it needs to be able to listen to every single person who can speak English from any part of the world with whatever accent, plus whatever domain that it applies to. It's not only the human spoken language in the world with different languages, but it's also the language of the enterprise that these models have to understand, because financial services language is very different from healthcare domain's language, and it's very different from retail's language, and the vocabulary is different, and therefore the amount of repetitions of these data that the model has to see for it to learn patterns, it's not possible to capture that when you're trying to build a broad model that works on everything. Of course, in an ideal world, that's the state we want to get to. That's the holy grail of AI, right? Solving the broad AI problem. But right now we are at a point where this is too hard. Therefore, we start to narrow the domain. So we say, okay, all right, I build the base model. My base model's accuracy may be around 70%, 80%. On any given problem, it may do reasonably well, but it's going to make mistakes. Then you say, okay, now I'm going to take that base model. I'm going to really give it very narrowed domain data. I'm going to give it healthcare data. And I'm going to give it a lot, as much as healthcare data I can get, and specifically healthcare as in a particular type, cancer related or a particular ulcer related. Then you are starting to narrow in the domain, and you're exposing more and more of that data to the model. So the model is seeing more and more repetitions of it to learn the patterns. And so it now starts to, on top of a pretty decent base, it starts to do a better job once you narrow the domain. And after that, each company, each doctor, each in particular company may have its own set of vocabulary and such that if you expose that to model, it will do even better. It will start to now further narrow the scope of domain where it needs to be really good at. And so what we have really noticed is that typically, if you draw a plot for precision curves, as the amount of training data increases, typically precision increases. Of course, it plateaus at a certain point. And if you say this blue line is the traditional base model learning curve, by narrowing the domain, that is on top of the base model, by taking industry specific data and customer specific data, if you start training it, you don't have to have as much of the costly base model training data. You can at any given point in time with a reasonable base start to ride these learning curves and get to higher levels of accuracy or precision faster with lower amounts of training data. So that is one of the key insights that we have noted early on, that when you can't solve the broad AI problem, tackle the narrow AI problem, and you can get to the learning, you can get to the same amount of accuracy that you want with fewer amounts of data, which tends to be the longest pole in the tent. So the goal is to reduce that so that companies can bring their models, AI models, out to the market quickly. So in this particular case, it may be a little hard to see. Actually, there is a video link on YouTube for this particular one, specifically with IBM's Watson speech to text, where after some training with just about a little bit of text data that you give the model and say retrain yourself, customize the model, immediately after that you give it the same speech audio file as input, and it makes far fewer mistakes. At least 4 of the 5 mistakes get corrected, and the model is now able to, with just about 2 paragraphs of text, because it has seen more specialized data, and the model retrain is set up in such a way that it retains all the base layers of learning and the understanding that it has, and it just adds this new amount of data that you have on top to the top layer, and it's able to reduce those mistakes. And this is what, so the strategy for increasing the accuracy in an enterprise, in building enterprise models, that we have realized is that build broad-based AI models in the first place, but narrow the domain to accelerate learning, and build AI models so that they can be customized for customers, and that way you can get to better accuracies. Okay, so now I'm going to talk about continuous learning. So let's say we built this model, we improved the accuracy by giving it to the domain specific data. Now we deployed it. Even so, its accuracy is not likely to be at levels that you want. You would want to be as close to 99.999% accuracy as possible. Every time a customer support person calls, when you deploy that chatbot or bot, you want to make sure that it understands everything that the user is saying, no matter how noisy the environment of that caller is in the background, no matter if children are screaming in the background, no matter if there is a train going in the background, right? You want the system to be that robust, and for that all to happen, it's not going to happen on day one unless, again, you spend all your time in training all sorts of that, and in which case you'll end up never releasing the model, because you're constantly in that state of making sure that, oh, I've got this corner case of children yelling in the background, I've got this corner case of some train going in the background, and so on, right? So you because enterprises are always in a hurry to get the models out and let them improve on the field, learn on the job, right? So humans do that a lot. So we want to make sure that the AI models can do it too, right? The first time around when we all tried to ride a bike, of course it didn't work out as we wanted. We fell many times, but then we learned from that falling which angle to balance ourselves in on a bike. So that's exactly what happens with AI models as well. So there's a lot of stuff in here. This itself we could spend an hour on it. So I'll kind of try to take you through what it means to continuously improve AI models. At the gist of it, there is an AI model that has been trained, and it takes some input, it makes some prediction. Okay. Let's forget about that explaining the results for the time being. It makes a prediction, and whatever this input that came in, let's say you log it, saying, I want to make sure that I log it. So the doctor's speech audio file, let's say, was the one that the system made a prediction on, prediction being the transcribed text, right? So we'll keep that audio file as we'll save it, because we want to make sure we compare it with the ground truth and see whether the model has got it right or not or whatever, and I'll tell you why more. Let's say it made a prediction. That prediction is either right or wrong. How do we know is the question. Oftentimes in real world, when you deploy it, nobody is sitting and telling you that that customer called with the intent of password reset, right? If that's what humans are doing all the time behind the scenes to verify whether this model got it right or wrong, humans might as well actually take that call instead of trying to give that feedback to an AI model. It's not feasible to do that kind of validation on every prediction that a model makes, right? It's just impractical. So what we do is how do we know if it's correct or incorrect? So we let a human actually give us that feedback for some time, during the pilot phase, let's say. Then we take that feedback and we build another AI model, let's say, that now sits here as an observer model and start to say, hey, this prediction based on the model that I learned from human feedback is either correct or wrong. So it's starting to make that classification. Of course, it itself could be wrong. It makes mistakes, false positives, false negatives, and sometimes if it is, even though the prediction is right, it could misclassify it. Even though if it's wrong, it could misclassify it. That's okay, but let's say as long as its accuracy is reasonable, you classify it and you take that in. Correct predictions you're okay with. Incorrect predictions is what you have to fix. Now you got to start going into the details of it and say, why did it get lower sternum as lower stardom? Why did it think troponin as whatever it said, troponin or proteinin or whatever the mistake that it made? That's the kind of error analysis, the systematic error analysis you have to do, and classify these errors into, it's the kind of error when there is too much background noise, it's the kind of error when there is a particular accented kind of user is speaking and therefore it's not able to get it. So you kind of start to really classify the errors that way. Now you're starting to zero in on where the model is actually making mistakes and you get a better idea. Then you take this input, right, because that is the input that you saved. Oh, that doctor's data is where it made a mistake. Therefore, you're going to take that and curate more of those kind of inputs, specifically that error you want to fix, and build a very specific model to address that problem, either by improving with that specific data of the same original model, or in some cases you may have different architectures where you say, I'm going to build a different model, and whenever I see that the input has the characteristics where the speaker's accent has some Spanish accent, I'm going to deploy this model, right? So you can start to make those kinds of architectural decisions, retrain and redeploy a new model. So the model has to continuously learn. That continuous learning can only be enabled if the model has the ability to reflect, as in it needs to know, it needs to have access to what it made predictions on, and it needs to be able to then reflect on it to say, what is the likelihood in which I got it right or wrong, and then do a very systematic error analysis. So actually the analogy, simple analogy that I would like to give is, when for those of you who have children or siblings, younger siblings, and you're trying to teach them, let's say they're making mistakes in long division, right? You give them a test, they bring home their math test, and you see, okay, long division mistakes, okay. So what is the strategy? You look at the scores and say, okay, this is the place where they are weak at, and therefore you now give them more test samples of that long division thing so that they get the hang of it, they learn that skill more, they get the concepts better, and then they're ready to give that test next time around and get better score on it. So it's exactly the same concept, right? You look at the predictions it makes, which is the test score in this math test, let's say, classify the errors, okay, long divisions problem, okay, fractions problem or exponents problem, whatever that specific things, you classify them. Then you give more examples of each one of those, let them learn that concept better, and then get them ready. So it's the same simple concept applied, but then you got to have the whole methodology built in a real world live deployed system. Because this thing is sitting, this AI model, this chatbot, for example, is sitting in a live environment, and you are observing. The AI model or the methodology that you have put in place is observing. It's looking at the data. It's building new models, new improvements in the background, and it goes through some human in the loop verification process, and then you deploy it in a different server, and then you decommission the old model, and you suddenly bring up the new model, right? It all has to happen seamlessly. So there is a lot of engineering stuff that needs to happen behind the scenes, but there is also a lot of continuous learning sort of AI stuff that needs to happen to continuously keep the models improving. So that's another factor that needs to happen. So this is one example. I'll go through this quickly. How much time do I have, Camille? Or
until 1. If you want to leave some time for questions.
Okay. All right. So this is one example where we are doing very systematic error analysis on our sentiment model, where we looked at the length of the text that came into our sentiment model and said, if it has 4 to 8 tokens or 8 to 12 tokens, let's divide it upon that dimension. And we noted that when the text is long, up to 144 tokens or words in it, our accuracy is low. So by slicing the dimension of input, we were able to identify the specific weakness area, and then we were able to improve through the continuous learning methodology that I have just talked about by deploying a new model. So whenever we get a long text, in order to predict sentiment more accurately on that long text, because it tends to have some neutral statement, something saying, oh, I like the service in that restaurant, but I don't like the quality of the food, or I like the ambience and the service, but the food was not good. So there will be some kind of those statements that were tripping up in a long sentence. So we were able to deploy another model that is very specifically catering to that kind of long text, and we saw that accuracy improved. So this is case in point example of how that continuous learning and the systematic error analysis that we have deployed actually improved the accuracy of an AI model. So the strategies for dealing with continuous learning are enable the continuous improvement via model customization with additional small amount of data as need be. Be very diligent with error analysis and fix the ones that matter, because you may not be able to fix everything in each iteration. And getting labeled data in large quantities could be a challenge. So one of the things that you have to think about is how to really work with small amounts of labeled data and let the model improve on top of the base. All right, let's talk about fairness. Again, I would say in the interest of time, I may not be able to go into depth on each one of these things as much as the first two ones I've covered. I'll go through them quickly anyway, and we can definitely follow up on questions. Fairness is a topic you could just get stuck in, like for 1 hour, 2 hours with all kinds of questions, right? It starts, there was this New York Times article that highlighted a piece of research that was done by some researchers who wrote an academic article in which basically most of the face recognition models in the industry failed to recognize African women's faces, and they failed so miserably. And so there was a lot of discussion that came up about how these AI models are racist or how they are biased. It's where do these biases stem from? If we look at that, biases can stem from the data that you have collected to train the model, or in how you have engineered the feature, which model you have selected. But for the most part, it's either in the data, training data or testing data. That's what most people kind of conclude. But one of the important insights that we got early on is that actually, even before you point the problem at data as the main bias source for building an unfair or biased models, it's actually the lack of goal setting is what I would argue. So if there was a good discussion before those face recognition models were deployed to say the objective is not to take whatever images that I got my hands on, train a face recognition model and deploy it and let it loose on the world. My objective is to be able to recognize all races, all kinds of human faces very accurately. First of all, let's say if that is your goal, versus inanimate objects or buildings, this and that and such. Let's say you set that as goal. If you have that as goal, then you would have created a very specific and representative test data set with all peoples from all parts of the world, races, everything represented, and you would have tested that AI model with that test data set, and you would have recognized that it fails at recognizing the faces of African women. So if the model was not specifically given a purpose and a goal and a test data set with some goal and threshold on how accurate it should be on that test data set, data scientists will do their best with whatever data they have access to, build a model, they'll deploy it. That's what ends up happening, and that's what ended up happening here. It's not that anybody actually purposefully wanted to build a biased face recognition model, or for the most part, most people don't go in with that attitude, although sometimes human biases may make their way into the data collection efforts and so on. But for the most part, it's that lack of clarity of purpose and actually very clearly defining that and very clearly capturing those test data sets to ensure that you properly test it, right? So if you don't know where you're going, every road will get you there. So if you don't have a purpose, and if you don't give very specific test data sets, and if you don't test it, of course, you'll just think that, okay, I reached my destination, and you deploy that model and you expose yourself to all kinds of criticism. So that's what ended up happening. So of course, we can go into the technical details of how to create unbiased AI models, how to test and all that. Today I'm covering the best practices and at a broader methodology perspective. So I'm leaving out some of the technical details, and you can refer to some of the work that IBM has done, some of the work that others in the industry have done, universities have done, and this is a hot topic for research. But among the strategies to mitigate unwanted biases, I would say set clear goals, start with test cases, declare your biases. Just the way the nutrition snack bars will tell you that you get 60 calories, 100 calories with this many carbs, this much fat, this much sugar, AI model should declare their biases. I'm trained with this much data of this kind, this variety, and my accuracy is such and such, and this is model version 1. If you provide all those details, the users will have a better idea of what they're consuming, and they can make their decision and judgment on whether this is the model that's right for their business case or not, right? And there are some standards and some guidelines emerging in the space of declaring fact sheets about AI models, and there is a lot of interesting stuff going on there, and again, that could be a topic in itself. So I'll leave it at that for biases. Quick few words on some of the other things, transparency and explainability. Now, this is again a huge area in the field of AI. Should AI models, or specifically machine learned models, be explainable? Now, you could argue one way or the other depending on the use case. It really depends on the use case. When we go to a doctor, we get a medicine. We don't specifically ask the doctor, right, about how the medicine actually works, what kind of proteins or compounds it breaks down into, how it interacts with our gut enzymes and all that. We don't ask all those questions. We kind of take the word for it that somebody has done that research, they did their tests, and it passed through some kind of an FDA approval, and that this is a safe enough drug for me to take, and therefore you take it. You don't ask for rationale and explainability. So some could argue that every AI model doesn't necessarily have to explain itself how it got to the prediction. That may work for some use cases, some domains. It may not work for some others. If you're on the receiving end of a loan application, and if the loan has been denied for you, and the company refuses to give you any kind of explanation on why their AI model refused to give you or recommended that you should be denied a loan, you are entitled to file a lawsuit against that company, and if you think you are being unfairly discriminated, and that company by law is required to provide explanation on how they got to that judgment. And therefore, some use cases in some industries, in some domains, there is a lot of legislation and a lot of legal policies that dictate the transparency of an AI model. In such cases, you have to make decisions on whether deep neural networks is the right architecture, right model for you that you may or may not be able to explain, or you may use more sort of a explainable, say, a linear regression, where it's transparent for you. What are the variables, what are the features, and what are the weights? So it depends on the use case. So among the strategies for transparency, explainability, understand your options and trade-offs, right? Deep learning models versus maybe just rules, business rules capturing. Or if you must build statistical deep learning models, then use black box testing techniques, which try to reconstruct the predictions that it made and why it made you can reconstruct it after the fact by questioning it a lot, and there are some techniques and a lot of papers on this topic. And if you use rule-based approach, you can explain it transparent, but to be careful in crafting the rules, and so there are approaches for doing that. But there are options, it's about learning that. So consistency is really, it's all about, you got to make sure that the model is consistently learning and not with every new problem it's trying to fix, new error it's trying to fix, it's not going back and is not unlearning something and making new mistakes, right? And that is an interesting point, because with statistical models you can never guarantee. It's what's in the data, the patterns that it's learning, it really depends on what data you have provided. So some of the strategies for that is really, do you need to guarantee the model improvements every time? If so, you have choices to make on statistical versus non-statistical models and such. Accountability and drift, I will, in the interest of time, skip. Robustness, I'll just talk about it very briefly. Models need to be robust, as in people can misuse them. People can manipulate the models by asking it with all kinds of data, and over time you can actually start to take that data and start to feed it into the model, and model not only starts to drift, and it could also be susceptible to different kinds of attacks. So for example, this was the image in the data set of a washer dryer. If you just change the angle of it, it could look like a safe, or it could look like a loudspeaker, or any number of things depending on how you change the angle. So one may actually make the model more robust by taking different types of these kinds of input data and teaching it how it works and so on. So I will kind of summarize across all of these things now, that first of all, AI models need to be accurate, right? And we talked about narrowing the domain and customizing your AI models. Next, about continuous learning. How do you make the models learn continuously? How do you make sure that they're fair, transparent, consistent, accountable, and robust with different kinds of strategies? We just went through this, so it's a quick summary of all of those things. So to sum up, I would say, it's to make those enterprise applications come alive, you really have to take not only just building the model, but all of these things into consideration, and perhaps several more. I haven't even gotten into security and privacy, and that's another huge area in itself. So with that, I'll conclude. Sorry, we're looking like going over a little bit. Open it up for any questions here.
Okay, we have about 10 minutes for questions. Is that okay?
Yeah, sure.
Okay. So we have one mic here and a mic in the back. Just raise your hand if you have a question.
Hi, thank you so much. That was really interesting. I'm curious if you can talk a little bit about maybe the debate around when it's appropriate to use social group categories like gender and race in kind of developing algorithms. So maybe some use cases where when might it be most appropriate actually to not use gender and race? It seems like generally it is appropriate. And then the next question to that would be, with different regulations coming down the pipeline, similar to GDPR, what are the kind of implications, and what should we be thinking about?
Okay. So for the first question that you asked, whether or not gender, race, those kind of attributes should be part of features of an AI model. It really depends, and in some cases they are genuinely discriminative in terms of what the model need to consider and make predictions on, and in some cases they could be discriminative in the wrong sense of being biased. If a human is making that judgment by taking all that data, would the human consider race, gender, and other things as important attributes is the first question to ask. The next question to ask is my data set typically representative enough across all the sections of society that the model needs to serve? And if it is not representative enough, then you be aware that it is likely to lead to biased decisions. Now, I have seen situations where some companies have actually explicitly stayed away from including those attributes as part of their model, even though they know that humans would use them in their own mind when they're going to give specific, loans or other things, because they felt that the models are likely to lead to likely to make unfair predictions because of the amount of data that they have. For example, young teenagers typically get higher insurance rates because there is a perception that they'll likely make more mistakes and they'll tend to make rash decisions. But that's a bias. That may not always be the case. So there are young folks who are very mature and who follow all the rules. So it really depends on the domain and the use case, and it's up to the decision of the human. Now, with regards to GDPR and the security, your second question of data and data governance and such, it's a huge thing in enterprises. That's in fact really kind of dictates how much data you can train your models with, how much data you have access to, and which regions can get access to what type of data. Even within the same company, if the data is in EU, you can only train the model in EU. Only the data that's in EU can be allowed to be exposed to that model, and so on. It cannot leave that EU premises. So there are a lot of data governance questions that come about that dictate the amount and kind of data that AI models have access to, and it's a huge deal. But it's an important concern to protect the privacy of individuals. Therefore, companies must take it seriously and must adhere to those things, and there is no two ways about it.
Hi.
Hi.
I have a question. I was wondering if you have an opinion about the autonomous driving race and the different approaches that have been taken. For instance, Tesla is collecting vastly more amounts of data by, through cameras in their cars versus, for example, Waymo, which is using LiDAR to collect much richer data, but much less data. Do you have an opinion on who's going to win?
Not specifically on that particular topic, but in general, I would say that, going back to the point on quality, it's about representative, good quality data in representative, labeled, good quality data in large quantities, right? These are the attributes for AI models. And those that can have that data in large quantities with all those criteria met will likely be able to build more high quality models. So in that situation, it looks like you have already outlined as to who has what kind of data, so you can probably conclude based on that. But in general, I would point to these attributes of data that's required to build more high quality models.
Okay, we have time for one last question here in the back.
Oh, yes, thank you.
Hi.
So you talked a little bit about the data sets, large enough data sets specifically, on the issue of bias. So we're interested in understanding some of the biases that have to do with, age, race, gender, but also disability. And I think one of your colleagues, Sherry Trowan, who used to work at IBM, was looking at those issues. What do you do with data sets that aren't yet developed? So people talk about people with disabilities being data deserts because there isn't enough data to represent. And yet I have a research center at Berkeley that had interviewed over 1,500 people with disabilities talking about their life stories. What could the data set of these 1,500 people with disabilities, how could those oral histories help inform a machine learning algorithm and AI engine to be more sensitive to the lived experience of people with disabilities in a way that wasn't repeating the same kind of biases or the same kind of other, normative approaches? And how do you take a group that might be considered an outlier and prevent them from being normalized in the larger data sets?
Yeah. So thanks for asking that. So I think it's about really first of all, you're doing a great service by actually creating such data set, right? And I don't know if you have made it publicly available, but if that data set is publicly available, then more and more researchers and academicians and industry folks will start to tap into that data to include it in their training of the models, right? So I don't know the specifics in that particular case, but yeah, that's one way, right? If there are specific points of view, specific attributes, or specific sections of societies whose data is underrepresented, efforts have to be made to collect data in those spaces and make it more largely available, and that's the only way it can be brought into the mainstream models. That's point number one. And to your second point of what was the second point? Sorry, what is it about using that?
Like
Outliers, how do you not normalize it,
so
right?
they're not erased by being averaged out.
Yeah. So some of it happens naturally through the amount of available data, right? So if in general, if there is not much representation of it in the questions that people are asking or in the inputs that the AI models are getting, they usually they usually are not exposed to first of all, they don't do a good job of that, first of all, because they are not necessarily trained enough on that data. But in the cases where it's important for the models to exhibit the same level of accuracy as on the rest of the types of questions that are coming in, then there is no going about it. We have to collect data, or we have to write rules, or we have to do something about it so that the model is able to address and answer and make predictions at the same quality and at the same level of accuracy as with the rest of the data. So I don't know if I'm specifically answering your questions on how do you not normalize, but if it is something that the model has to make prediction on and you expect a certain level of accuracy, there are the same set of considerations that you have to go through in terms of the pipeline as to what precautions you would take so that the accuracy in making that prediction for that particular type of query is just as good. But there will, or you may have separate strategies for dealing with the long tail type of questions, because it's a very well-known thing in search domain that you optimize the search model for the most frequently occurring questions, but then you have a specialized model or specialized thing that kicks in for long tail type of questions. So maybe there something could be done in AI models as well. And that's the one example that I alluded to when I talked about sentiment example, where I said in the cases where we have long text, where the model is not doing well, we figured out that through a disciplined error analysis, and then we said, let's actually have a router where whenever we discover this long text, we are going to let the model pipeline go through this other model, because that's the one that's specifically trained to process it. So there could be strategies like that one can think about to deal with outliers.
Thank you very much.
Thank you.
Okay, thank you, Rama, so much for coming and joining us today.
My pleasure. Thanks again.